Welcome viewers to the sixth lecture for the online series of lectures for the course of linear algebra. In this lecture we are going to continue our discussion on basis and dimension from the fifth lecture. So we will discuss basis and dimension continued from the fifth lecture. Okay, so we'll start with the result. Let me state the result first. Let S be a linearly independent subset of a vector space V. Suppose V is a vector which is not in the subspace spanned by S. Okay, so there is this vector space V inside which there is a linearly independent subset S, and we have a vector V that is not contained in the subspace generated by this linearly independent subset S. Okay, it lies outside this subspace. Okay, then the set one obtains by adjoining V to S is linearly independent. Okay, so we need to prove that this set S union this vector V is linearly independent in V. Okay, so here goes the proof. Suppose U1, U2 all the way up to UM are distinct vectors in the linearly independent set S. Okay, and also we suppose that the following holds: alpha 1 U1 plus alpha 2 U2 plus all the way up to alpha m UM plus beta V is equal to the zero vector. Okay, is the linear combination of these m plus 1 vectors, m vectors from this set S and the vector V. Okay, so let us number this equation by 1, where these alpha i's are all in the field F over which the vector space is defined, and beta is also in the field. Okay, where V is defined over F. Okay, now one would imply that beta is equal to 0. Why? Because if beta is non-zero, then we can write beta V to be equal to minus alpha 1 u1 minus alpha 2 u2 all the way up to minus alpha m um, right? Okay, and if beta is not equal to 0, then we can divide both sides by this non-zero scalar to obtain vector v to be equal to minus alpha 1 by beta times u1 plus minus alpha 2 by beta times u2 plus all the way up to minus alpha m by beta times um. Okay, which results in the fact that V belongs to the subspace spanned by these M vectors. Okay, contradicting the hypothesis that V does not belong to um, the subspace spanned by the set S. Okay, so which means that beta is non-zero. Which means that beta is 0, right? Otherwise we would have a contradiction. Okay, let me erase everything. So beta is going to be equal to 0 in 1. So then equation number 1 reduces to alpha 1 u1 plus alpha 2 u2 plus all the way up to alpha m um is equal to the 0 vector, right? Now remember that this set S is a linearly independent set, and u1 u2 all the way up to were considered distinct vectors in S, right? So which means that this set is a linearly independent set in the vector space V, and hence all these scalars should be identically 0. Alpha I is equal to 0 for all I. All right? So if we number this equation by 2, then in 2 all the alpha i's are 0. So now if we combine these results, then we see that for the vectors u1 u2 all the way up to and the vector v, alpha 1 u1 plus alpha 2 u2 plus all the way up to alpha m plus beta v is equal to the 0 vector will imply all the scalars are identically 0. Okay, since the distinct vectors u1 u2 all the way up to in the linearly independent set S were chosen arbitrarily, the set obtained by adjoining B to S is linearly independent, right? QED. Okay, now we state our next result by means of a theorem, which is theorem 1. Then we'll prove it. Okay, it states that if W is a subspace of a finite dimensional vector space V, every linearly independent subset of this subspace W is finite. Okay, and is part of a finite basis, right? Okay, so here goes the proof. Suppose S0 is a linearly independent subset of this subspace W, linearly independent subset of W. Okay, right? And since W is a subspace of the finite dimensional vector space V, S0 is also a linearly independent subset of the vector space V, right? Then S0 is also a linearly independent subset of the finite dimensional vector space V, right? And since V is finite dimensional, S0 contains no more than dimension V elements, right? Since V is finite dimensional, okay, and if we note the dimension of this finite dimensional vector space V by dimension of V, then S0 does not contain um, uh, more elements than dimension V, than the number dimension V. Okay, so that way we see that a linearly independent subset of W is finite. Okay, now we need to prove that it's part of a finite basis. What does it mean by a part of a basis? It means that if we start from this linearly independent subset S0 by including finitely many elements to this finite linearly independent set S0, we can construct a basis of the subspace W. This is what it means by part of a finite basis. Okay, so in other words, we need to prove that the linearly independent set S0 can be extended to a basis for the subspace W. Let us see how we can prove this. Let me erase everything. We extend the linearly independent set S0 to a basis for the subspace W as follows. If S0, the linearly independent set that we started with, okay, if this guy spans the subspace W, then we are done. Then S0 is a basis for W, right? Because if S0 spans W, by hypothesis, S0 is linearly independent. Hence, S0 is going to be a basis for W, right? And we are done. But if it's not the case, that means if S0 does not span W, then there is a vector W1, let's call it W1, in W that is not contained in the subspace of W spanned by S0. Okay. Okay, so it's guaranteed that we can find such a vector W1 if S0 does not span W. Okay, so it's guaranteed that there exists such a vector W1 which is not contained in S0. Okay, now by lemma 1, which we proved a while ago, the set S1 equal to S0 union this singleton W1 is linearly independent, right, in W. Now, we have found a linearly independent subset in W, S1. Now, if S1 again, similarly, if S1 spans W, now we have found a new linearly independent subset, a bigger linearly independent subset, so to speak. If S1 now spans W, we are done, right? If not, then again one can find a vector W2 in W that is not contained in the subspace spanned by this subspace S1. Okay. Now, using lemma 1 again, one concludes that the set S2 is equal to S1 union this singleton W2 is a linearly independent set in W, is a linearly independent set in W, right? So if one continues this way, so in no more than dimension v steps, one reaches a set like this: Sm is equal to S0 union W1, W2, all the way up to Wm, okay, which is going to be a basis for the subspace W. Okay, this is going to be a basis for W. So this way we see that S0 can be extended to a basis of W. In other words, S0 is part of a finite basis of W. S0 is a part. This is what we mean by part. Part of a finite basis of the vector subspace W. Okay, QED. Good. Now a bunch of corollaries of theorem 1. There are 3 corollaries. We are going to prove one of them only, and the rest are left as exercises. Okay, so this is corollary 1 to theorem 1. Which states that if W is a proper subspace of a finite dimensional vector space V, vector space V, then W is finite dimensional and dimension of W is strictly less than dimension of V. Okay, so here goes the proof of this corollary. So we may suppose without loss of any generality that there is a non-zero vector U in W, right? Okay. So then, according to the proof of theorem 1, we can construct a basis for W that contains this non-zero vector U. In other words, U will be part of a finite basis of W, right? One can construct a basis of W containing this non-zero vector U such that the basis contains no more than dimension V elements. Okay, so which means that W is finite dimensional, right? Hence W is finite dimensional and dimension of W is less than or equal to dimension of V. Okay, so there is an equality here that needs to be excluded, right, in order to prove this. So this is equation 3. Okay, now since W is a proper subspace of the finite dimensional vector space V. There is a vector V in the vector space V such that V is not contained in this subspace W. That is, V does not belong to a basis of W spanning W. Right? So hence by lemma 1, one can adjoin this vector V to the given basis of W to find a linearly independent set in the given vector space V, right? So let me write it here. Hence by lemma 1, the set one obtains by adjoining V to the given basis of W is a linearly independent set in V, the cardinality of which is going to be dimension W plus 1. Okay, so let me erase this front matter. So we have seen that we can have a linearly independent set of dimension W plus 1, right? Since dimension V, so we can have a subset. We can have a subspace of the finite dimensional vector space V whose so we can have a linearly independent subset of the finite dimensional vector space V of cardinality dimension W plus 1. Okay. Since dimension V is the cardinality of the maximally linearly independent set of V. Okay, so if one has a linearly independent set from the given finite dimensional vector space V, the cardinality of this set is not going to exceed this number dimension of V. Okay, that's the maximal number. That's the maximal cardinality of a linearly independent set of the of the given vector space V. Okay. Therefore, since this is the maximal number possible for a linearly independent subset of a given vector space V, dimension W plus 1 is going to be less than or equal to dimension V, which means that dimension W is strictly less than dimension V. This is how we get to the strict inequality. All right, QED. Good. Now the second corollary to this theorem 1, which I am going to state without proving it, and the proof is left as an exercise. Corollary, which is an easy exercise. Corollary 2 to theorem 1. In a finite dimensional vector space V, every non-empty linearly independent set of vectors, okay, is part of a basis. Part of a basis. Very easy proof, okay, which means that if you choose a non-empty linearly independent set of vectors in a finite dimensional vector space, then that linearly independent set can be extended to a basis of that given finite dimensional vector space. All right. Now, corollary 3 to theorem 1, which states that if A be an n times n matrix over the field F, suppose the row vectors of this of matrix A form a linearly independent set of vectors, linearly independent set of vectors in F to the n, okay, n tuples where each of the coordinates or components of that n tuple is a scalar, okay, Fn, then A is necessarily invertible. Okay, so the proof is left as an exercise. Okay, good. Now the second theorem, an important theorem that we are going to state and then prove, theorem 2, which states that if W1 and W2 are finite dimensional subspaces of a vector space V, then the sum set denoted by W1 plus W2, which is defined to be the set of all vectors of the form W1 plus W2 such that W1 belongs to big W1 and W2 belongs to big W2. Okay, then this sum set, which can easily be seen to be a subspace, right? So this sum set is finite dimensional and dimension of W1 plus dimension of W2 is equal to dimension of this subset, subspace W1 intersected with W2 plus dimension of this subset W1 plus W2. This is what one needs to prove. Let us see how the proof goes. By theorem 1, okay, which we proved a while ago, and its corollaries, the subspace, okay, which one can easily check that it's a subspace. The subspace W1 intersected with W2 of both the finite dimensional vector spaces, finite dimensional vector spaces W1 and W2 is finite dimensional, right? So W1 and W2 are finite dimensional vector subspaces of the given vector space V, which means that W1 and W2 are both finite dimensional vector spaces, okay? And W1 intersected with W2 is a vector subspace of both these finite dimensional vector spaces W1 and W2. Okay, so since it's a subspace of a finite dimensional vector space, either you can take W1 or you can take W2. Therefore, this vector subspace W1 intersected with W2 is also finite dimensional, right? So it has a finite basis. So let us denote this finite basis of W1 intersected with W2 by U1, U2 all the way up to UL. Okay, this is the basis of W1 intersected with W2, right? Now, according to theorem 1, this guy can be extended to, since this is a finite dimensional vector subspace of W1, and this guy is a basis of W1 intersected with W2, then according to theorem 1, this set, and this is a linearly independent set, of course, and this can be extended to a finite basis of W1. In other words, this guy is a part of the basis of the finite basis of W1. So let's write that basis of W1, U1, U2, UL. So this is the linearly independent set that one starts with. Then we have to adjoin vectors to complete the basis of W1. So let's adjoin vectors V1, V2 all the way up to Vn to have a basis for the finite dimensional vector space W1. Okay, and also since this guy is a basis of this finite dimensional vector space, and this finite dimensional vector subspace is contained in the finite dimensional vector space W2 as well, then this guy can be extended to a basis of this finite dimensional vector space W2. Let's write that basis of W2. So this is the set, linearly independent set here, which is a basis, and that can be extended to that a basis for W2. So let us adjoin vectors w1, w2 all the way up to wn, okay, to form a basis of w2. These we can do using theorem 1, right? All right. Now, so this guy is a basis for w1 intersected with w2. This is a basis for w1, and this is a basis for w2. Okay, so we have three sets of bases, okay, for each of these subspaces of V. Now the subspace w1 plus w2, okay, which can easily be shown to be a subspace, is spanned by the vectors belonging to the following set: u1, u2, all the way up to ul. So I'm just taking the union of all these vectors here, okay, and that confirms that subspace w1 plus w2 is going to be spanned by the union of all these vectors. So ul, and then v1, v2, all the way up to vm, and I'm going to adjoin w1, w2, all the way up to wn. Okay, so w1 plus w2 is going to be spanned by these vectors. Now the claim is that this set is a linearly independent set. Okay, suppose alpha I ui, we take the linear combination of these L vectors I from 1 to L, and we also take the linear combination of these M vectors beta j vj, where j runs from 1 to M, and gamma k wk, where k runs from 1 to n. Okay, so this expression is equal to the zero vector. Suppose this holds. This is our equation number 4. For alpha I, beta j, and gamma k being in the field. All right, so let me erase the part here. Okay, then from 4 can be rewritten as minus gamma k wk, k from 1 to n is going to be equal to sum over alpha I ui, I from 1 to L, plus sum over beta j vj, j running from 1 to m. Okay, this is what we denote by 5. Okay, and it immediately shows that these vector here okay, which shows that, so we are writing this guy on the left as a linear combination of the vectors u and v, right, we, which constitute the basis of the vector space W1. So this shows that this vector sum of all these expressions gamma k wk, where k runs from 1 to n, belongs to the vector space W1. Okay, good. Now um, this but it's important to know that um, since these vectors w's, right, are is a part, if you take the of all these wk's, the set that you get is a part of the basis of w2, right, and hence this vector, which is a linear combination of all these w's, this vector belongs to w2. Belongs to w2. So this guy belongs to W1 and also it belongs to W2. Hence this guy belongs to the intersection of W1 and W2. Hence sum of all this expression gamma k wk, where k runs from 1 to n, belongs to W1 intersected with W2. And we know that the basis for W1 intersected with W2 is the set containing all the u's. Okay, u1 u2 all the way up to ul. This is the basis of w1 intersected with w2, and since this guy belongs to w1 intersected with w2, we can write this guy sum of gamma k wk, where k runs from 1 to n, as a linear combination of these vectors in this basis of w1 intersected with w2, right? So let us write this linear combination as the sum of all rho I ui as I runs from 1 to L. Okay, this is equation number 6. Now, since this is a linearly independent set, the set of all u's and the set of all w's is linearly independent. From 6, one concludes okay, so these vectors together form a linearly independent set in the given vector space V. Okay, which means that all these scalars need to be identically 0, right? Gamma 1, gamma 2, all the way up to gamma n, right, is equal to rho 1, rho 2, all the way up to rho L is equal to 0. This is our equation number 7. So using 7 and 5, what was 5? Okay, this was 5. Right? So using 7 and 5, one obtains 7 and 5, one obtains so you plug in gammas to be 0 here, and you also plug in, okay, and so you plug in gammas to be 0 here, there is no rho here, so that one has the sum over all alpha I ui plus the sum over beta j vj. Okay, here I runs from 1 to L and j runs from 1 to m. Okay, this is the 0 vector. So I just plugged in gamma to be 0 in this equation 5 to get this. This is our equation number 8, right? Now we know that this is a linearly independent set. The set of all the u's and the set of all the v's, okay, is also linearly independent, right? Because this was a basis of W1, remember? Which means that this is a linearly independent set. So since this is a linearly independent set from 8, it follows that all these scalars should be identically 0. Okay. So one has alpha 1, alpha 2 is equal to alpha L, right, is equal to beta 1, beta 2, all the way up to beta m is identically equal to 0, right? This is our equation number 9, right? Now 4, 7, and 9 together imply whenever we are given this, or whenever this is satisfied, the sum of all these expressions resulting in the 0 vector, the sum of all these expressions beta j vj, where j runs from 1 to m, plus the sum of all the expressions like gamma k wk, where k runs from 1 to n, is equal to the 0 vector. Whenever this is satisfied, one ends up with alpha 1 equal to alpha 2 all the way up to alpha L, right? This one is equal to beta 1 is equal to beta 2 all the way up to beta m, and these are also zeros, is equal to gamma 1 is equal to gamma 2 all the way up to gamma n is equal to 0, right? So which means that which means that the set of all u's, u1 u2 all the way up to ul, the set of all v's, v1 v2 all the way up to vm, and the set of all w's, w1 w2 all the way up to wn. So the set of all u's, all v's, and all w's, this set is a linearly independent set. Independent set. Okay. Also, this set above here, okay, this guy spans the sum set w1 plus w2, okay. Hence, this guy is a basis of this subspace w1 plus w2, the sum set. Okay. Finally, we write dimension of w1 plus dimension of w2. So remember that in the basis of w1 there were how many sets? Sorry, how many elements? There were how many elements in the basis of w1? In the basis of w1 there were L plus m elements. So dimension of w1 is L plus m, right? And there were L plus n many elements in the basis of w2, right? L plus n many elements in the basis of w2, right? So it means that this is equal to L plus m plus L plus n, okay. And well, what was the basis of w1 intersected with w2? It was u1 u2 all the u's, right? That was the basis of the subspace w1 intersected with w2. So so L is the dimension of that subspace, dimension of w1 intersected with w2, okay. And what is this? Um, um, the sum set, right? The sum set is also a subspace, and we have shown that the dimension of this sum set is precisely, since this is a basis, the dimension of this is the basis of this sum set w1 plus w2, and hence the dimension of this sum set is equal to L plus m plus n, right? So this guy is the dimension of w1 plus w2. This is what we needed to prove, right? QED. All right, now I suggest some exercises based on what we have discussed so far on bases and dimensions. Suggested exercises. They are suggested from the book by Hoffman and Kunz. Page 48. Problem number 1, 2, 3, 7, and 11. Okay, so I'm suggesting only 5 problems. You should try to work them out. Okay, so it's a good time to take a break, and we'll be back with this concept of coordinates in the next segment. Thank you for attending this first segment of the sixth lecture.